greatly diminished. Okay, first question. Do you guys want to move on, or people want to see an example of how to compute one of these frames for a function? I realized at the end of the time last time that I was treating this class temporarily like it was a class in theory, and I hadn't actually worked all the way through an example. Do people want to see an example of how you work through one of these things? Because I got home and I was like, I never actually did it. I talked about it and I never did it. So let's do one. Now, these very frequently are not possible to work with by hand. So it's going to be the case that the example that we work through is not very complicated, but at least it's the sort of exact example that you're going to have to do. So at least it's illustrative enough to actually do it. So let's look at this. So this is an example of how to compute a T and B frame. Okay, so let's look at x of t. Numbers or letters for the coefficients on this thing? You want a real general case, or you want something concrete? Numbers. All right, concrete it is. X of t is equal to what was the one I got corrected on last time? 3 cosine t, 3 sine t, 2t. Oh damn! Hold on. I'm gonna make this easy on myself. I'm gonna put a 4 right here instead. Now, why would I do that? Because there's going to be an a squared plus b squared. It's going to have to take a square root of it at some point. So I might as well set it up so the Pythagorean theorem works. Okay, so let's actually compute the frame. So compute moving frame. What's that? 2, well, no, because 2 squared plus 3 squared gets you 13, and the square root of 13 is the square root of 13. So unless you guys want root 13s all over your notes. If I do it this way, it'll be 5, which is nicer, right? I mean, it's all the same, but we're going to read the frame. Oh yeah, I mean, setting up so that it's easy to compute on the board is a big part of choosing examples in class, right? It's like you have to adjust things so you don't have to do math. I mean, the trivial math, the arithmetic. Okay, how do we compute t? So what is a moving frame? That's the first thing. So to compute a moving frame, we are being asked to find t of t, n of t, and b of t. How do I do it? What is t of t? T dt divided by.
So the length of that?
Yeah, the length of the derivative, right? You can either think about it as ds dt dt divided by ds dt, which is the same as dt dt divided by the length of x. How do I get in? So n measure, even if you don't remember, you can figure it out. N measures change in the tangent vector. So we're going to do dt, but now it's supposed to be a unit normal vector. Sorry, this is supposed to be dx dt. Sorry, my bad. It's a differential equation involving the tangent vector. No, sorry, my bad. Yeah, it's velocity divided by length of velocity. V divided by the length of the vector. It's all the t of t. Okay, then I have to keep track of the direction of this vector, how that's changing. So I take its derivative, but it needs to be a unit vector, so I have to divide by its length. And then the binormal cross product. It's got to be perpendicular to the other two. Which cross product?
T cross n.
Why t cross n and not n cross t?
Right.
It is. I mean, yes. Convention is the answer. We wanted to satisfy a right-hand rule, basically, right? That's ultimately what it is. So t cross n. If you do it, are you going to totally tank your problem? No, you're going to get the negative of the answer, right? So you'll flip the orientation of your system if you do that, which is bad if you're working in a field where the convention is one way and you flip your orientation around, right? This is related to the whole thing about where electrons all move backwards from the way that formal electricity works. If you guys have not seen that fact yet, like, oh yeah, like the way we mathematically do circuits in our classes, the actual electrons, if such things could be said to exist, are actually going in the other direction. Because when they figured out the theory and set all the conventions up, they didn't actually know what electrons did or were. And it turned out that they were wrong by a negative sign. Anyway, some people find that kind of alarming. A lot of convention in science. Okay, so for us, this is the function we're going to work with. We're going to start by computing t. T is supposed to be equal to x prime over the length of x prime. Since we carefully chose a helix, we're going to get, let's see, x prime of t is equal to minus 3 sine t, 3 cosine t, 4. It's a good thing I picked that 4 right there. Okay, derivatives work entry-wise when working with vector maps, remember. So if I have d by dt, a regular old derivative of a vector value map, I can just push the derivative inside. That has to do with the way that like vector arithmetic works. If you want a cute exercise to yourself, you can, here. For the math majors in here that are bored and don't have enough math to do, a cute exercise is to prove that d by dt of x of t, y of t, z of t is equal to x prime of t, y prime of t, z prime of t. And I know all you guys have nothing better to do than write down limit definitions of derivatives in your spare time, but it's a thing you could do. What is the length of x prime? So square root of 9 sine squared. Is it okay if I just skip the part where I squared the thing? And then the square of this is 9 cosine squared plus 16. Oh, what happy circumstance. Square root of 20. Why is it square root of 25? Sine squared plus cosine squared is 1. So you can factor out the 9. 9 times 1 is 9. 9 plus 16 is 25. And oh, a 5. Okay, so that means that t is equal to 1/5 of this vector. Right? And you might ask, do I have to push the scalar inside? And the answer is generally it's best practice to do that because we're going to have to take more derivatives, and the more stuff you have inside and outside, the more chances there are to make mistakes or forget stuff, right? So you should really write this as that also will help you convince you that this is a unit vector. That's a good self-check, by the way, as you're working your way through these exercises. Because if you stop at any point and you get something that's not a unit vector out as something that's supposed to be, then something has gone very wrong. Okay. All right, there's t. We'll try to draw this when we're finished. What's n? Okay, so dt dt over the length of dt dt. It's almost like I built this problem to use the Pythagorean theorem over and over again. Okay, so what is the derivative of this vector? Well, the 3/5 don't change. Derivative of sine is cosine, so we're going to get minus 3/5 of the cosine of t minus 3/5 of the sine of t, and then 0. Divided by the length of that vector. Okay, what is the length of this vector? It's going to be the length of this vector. Length can't be negative, right? If the length of cosine sine, the length of that vector is going to be 1, right? Cosine squared plus sine squared is 1. The length of this vector turns out to be 3/5. The reason is that this has length 1. And so you can pull out the 3/5 here. The reason you don't pull out the negative is because when you take the length, you would apply absolute value to that, which would turn into a positive 3/5. And so n is equal to minus cosine t minus the sine t 0. Now already, this is already kind of there's something we can interpret here about the behavior of the helix. Remember, what we're describing is the motion of a particle traveling a helical path. So that function x, that path x, is sending a particle like this. We're going around in a circle, and then the z value is making us go up each time, right? So it's twisting like this, but also it's traveling up in the z variable. So it means something. What is the fact that there's a 0 here in the z coordinate of this normal vector mean? So it's a plane, but it's a plane oriented how? Oh, you were asking a question. Sorry, let me go over here. You had an answer. It's no change in the orientation of the turn. So even though this thing is twisting through space, this might be kind of counterintuitive. The turn is always a flat turn in the xy plane. So at any given point, the path feels like it's a flat turn, right? So it's going up. Even though this thing is constantly increasing its altitude, the plane of the turn is always parallel to the xy plane, which is a strange thing to think about, right? Like, there's something about the way the forces are acting here that's pretty odd. So,
I was just going to ask
yeah, so because we talked about yesterday, we talked about the decomposition. So there's a radial velocity and a radial acceleration associated with it. Yeah.
I was just going to say that, you know, the word z velocity, right?
That's really what the issue is here, right? So like, yeah, so what this describes, this vector t, this describes your velocity in space, right? It's the direction of your velocity, but the direction of your velocity is always constantly equal to 4/5. Nothing's varying in that at all. So you don't have any sort of vertical, there's no sort of vertical component to the way that your velocity is changing. And what that means, if the vertical component of velocity never changes, then the perpendicular vector that can never change direction. So you sort of fix. It's weird. You're going around. It's like you're doing this, but this vector always feels like it's always pointing straight up. And that means you can think about it this, it rotates. It rotates around this vector, but it doesn't change it. So yeah, this is not a flat, it doesn't look like a flat turn, but this is a flat turn. And if you think about it for a second, this is actually why they bank. This is why they bank tracks for cars actually. So like, even if you did something like this where you twisted, the forces the car feels are flat turn forces. Weird. Anyway, that's an aside. Okay, so we got n, we have t. The n vector means that we're looking at flat turn. What's the b vector? Am I actually going to make you do that? Come on, you got to take the cross product. T cross n. It's good for you. Talk about eating your spinach in here. This is it's a spinach eating exercise. You got to get in there and compute a cross product. All this stuff you have to do once by hand so that you appreciate computers for the rest of your life. Yep.
There was like a trick that was cross product where it's like
oh my god. Okay. Yes. You're right. You can do the three.
I don't know the diagram.
That's why I'm not going to teach it to you. So there's a trick. I mean, I am happy to show anybody how that trick works, right? Like if you've ever seen the thing where you add 2 extra columns and you go up the diagonals and down, it works.
Oh yeah.
Right. But most of you are going to have to compute derivatives that are larger than 3 by 3 in your lives, and you should really learn derivatives. I mean, I know God help you that you got to do that, but it is a thing that you have to do is work with derivatives of matrices. And if I give you a derivative formula that only works in 3 dimensions, it's like I'm cheating you in some sense, right? It's great that it works, but it doesn't hold up in higher dimensions. So let's compute it without doing that. So t cross n, maybe it will be easy. I, j, k, what's n? Where's t? Where's t? Minus 3/5 times sine minus 3/5, sorry, positive 3/5 times the cosine and a 4/5 right here. At least we'll get 1 0 minus the cosine minus the sine 0. Oh, how depressing. Well, we might as well do it. Okay. So what does this turn out to be? Oh, the cosine disappears because I times this little determinant right here. The 3/5 cosine hits the 0 and vanishes. So remember the way you do this is it's I times the determinant of this little matrix, which is those things multiplied on the diagonals and then subtracted. So you get I times 0 plus 4/5 of a sine t. Well, that's nice. Minus j. So j is these guys. So it's this thing, which is 0. This thing, which is minus 4/5 of a cosine.
Plus. Oh, minus. Plus.
Yeah. Well, what I'm doing here is I'm saying it's j times this minus this times that, which is a plus cosine of 4/5. A k vector that is, hold on a second, plus k times 3/5 of a sine squared. Those are both negative, right? And then we subtract off a negative 3/5 of a cosine squared. So it's plus 3/5 of a cosine squared. Oh, cool. This is just 3/5. And the vector that comes out at the end here is 4/5 of a sine of t minus 4/5 of a cosine of t and 3/5. How do I know that I've gotten this right? If I have gotten it right. Maybe I haven't. They're all pairwise orthogonal. It's a good way to check, right? Yep. Probably. Let's see. Maybe. So there's a j right here. And what I did was I took this times this and this times this. Is it supposed to be positive?
Oh, no.
Because this is the positive term, which is 0. Then you multiply by these guys, which is minus 4/5 the cosine of t, but then you subtract it, which turns into a positive. But then the j takes the negative sign, which turns it back into a negative.
Wait, j takes a negative sign?
Always.
J
Whenever
minus-
you're doing a determinant, there's always this thing called the sign matrix running around in the background that tells you what to multiply the entry by. So the reason this is whatever's up here with a positive sign in front of it times the determinant of those two guys. Whatever's up here times a negative sign in front of it times the determinant of the other two. So the rule is it's always plus I minus j plus k. Okay.
Why is that?
You really want to know? Okay, you know what? I'll tell you just, you open a can of worms, I'll tell you. So the reason is because really the determinant secretly, and this is points to an important question. So the determinant as a function is really weird because it's a thing that's defined on the family of all square matrices simultaneously. And that's weird that it can take all kinds of different inputs, right? And so it turns out to be like, if you look at like something in group theory, that if you want to define what it means to be a function on all matrices of all sizes, there's a way to think about it as a map on all the set of all permutations of n elements. And it induces this sign matrix to be consistent from like size to size. So that's total non-answer, but it's a deep question why the sign matrix happens, right? There's a lot of algebra that goes into why this is true. So you might see it if you take a modern algebra class or a number theory class, you might see why the determinant is defined. And if you really want to know, I can send you a little chapter from one of those books. You can dig right in. Anyway, I think I've computed this correctly. Did I? I mean, we could check. What was t? I'll throw t away. Okay, so this is going to be minus 12/5 sine squared minus 12/5 cosine squared, which is minus 12/5 plus 12. Okay, cool. It's at least it's perpendicular, right? I'm still happy. This is perpendicular to that. I only have to check one. Clearly, it will be true for the other one. So what I did really quick here is this vector right here. This is the b vector, and I checked to make sure that b was perpendicular to t by taking the dot product. That's all I did. B dot t is equal to 0, and notice it's automatically a unit vector. And that's an example of how I compute a moving frame. Now, normally when you do this in a computer, it just hooks up this frame for you. And one of the things I'll show you guys when I get a chance to sit down over the weekend is I'll build a demo that actually does this on a more complicated function, so you can see how the rotations can happen. And then I'll show you how the force stuff hooks into it too, so that the velocity and acceleration vectors are recovered by taking the T and B frame and then applying those the acceleration and velocity to it. Okay. So if the question says find the moving frame, we get all the way to the end. What did we actually do? We found that T was equal to minus 3/5 sine T 3/5 cosine T 4/5. We found that N was equal to minus the cosine of T minus the sine of T 0. And we found that B was equal to, where did I put it? 4/5 of the sine minus 4/5 of cosine and 3/5. The point of having this is that you might think, okay, well, that's a lot of work. That's really what I get out the end. What the hell does that even mean? Remember that the idea here is these completely describe the motion of the particle traveling through space. If you give me any T value, I can tell you the direction that you're headed, the direction you're turning in, and there's something that describes how the twist is going to be happening, because the derivatives of all these things matter. The derivative of this is acceleration, the derivative of this captures the notion of curvature, and the derivative of this, or sorry, the derivative of this captures acceleration and curvature, the derivative of this guy gets you torsion. So motion is entirely described by this. Okay. Now, I will tell you that it is very difficult for me to give you a question to do with these that is any different than the helix. So if I ask you to do this, I should say when I ask you to do this, it'll either be polynomials or it's going to be a helix, because anything else basically requires a computer. It's related to the idea that like the square roots start getting so bad you just can't work with them. Okay, any questions about that before we go on? Notice that this glues together all that matrix stuff that we talked about at the very beginning of the class, right? Since this is a vector class, you have to learn how to work with vectors. Okay, 208, 211, 213, arc length and differential geometry. Get out of here. Okay. Let's start with a definition. This is section 3.3. So we are moving on to the study of vector fields. So the first thing I'm going to define is what it means to be a scalar field. So this is the definition. F taking some domain from Rn into R is called a scalar field. The analogy I made here is like a temperature map, right? We talked about surfaces before, but I don't want you to think about surfaces floating in space anymore. I want you to think about, you take some set in your input space, and to each point in your set, you assign a number. So I really want you to think about these things as being like temperature maps. Or if you don't want temperature maps, I want you to think about them as, some people like to think about these things as equipotentials, doing a lot of electricity. You might think about a topographic map. So like I don't know, topographic map, where to each point you're assigning an altitude, however you like to think about it, right? You've got some field, there's some set of numbers, set of points. To each point, you're putting a number on, and then not tripping over your keyboard. So every time you look at a weather map, you're looking at a scalar field, as distinct from a surface, which is the way we think about this before, floating in space, right? So let's look at what the hell. We'll put the book in this order. Okay. So the very next thing we're going to find is an object called a gradient field. So you get a gradient field by taking a scalar field and taking its gradient. I can find a function if I have f of x is a scalar field. F of x is a scalar field. Say f takes R3 into R. What sort of object do I get if I take the gradient of f? Like, what is the gradient of f? If I actually computed grad f, gradient of f, what is this? Somebody tell me what it, I mean, by definition, what is this?
Direction, gradient.
Okay, yes, but like, how do I compute it? Fx, yeah, good. Fx,
FY.
Fy, Fz. So the gradient of f actually assigns to each input a vector instead of assigning a number, right? The gradient of f is a vector field. This is a function that assigns to the point x, y, z the vector fx, fy, fz. You fit it an input, it produces this output. It's the most natural way of coming up with a vector field. Like, you know, let's actually see if we can understand what's going on here. How would this operation get me? When I think of a vector field, I think of, okay, I've got a bunch of points x and y, and everywhere gets a little arrow attached to it. And then the function that assigns the arrows to the points is the vector field. How on earth do we get from a scalar field to a vector field by the use of a gradient? And the answer is, if you think of a scalar field, and you take all the level curves of a scalar field, and you take the gradient at every point on all of the level curves, what do you get? Well, at each point, you get the gradient vector. And everywhere you take a gradient against every single possible level curve, you're going to get the direction of greatest change, right? So I should be doing this in two different colors of chalk. Let's live large in math class. So the idea is the original function in white here, this function, the f of x and y, this is the scalar field. Because what it did was it took every input value x, y and assigned a z to it. So this point right here has a z attached to it, and this has a z value attached to it, and this has a z value attached to it. There's a scalar attached to it. If you take the gradient of f, that's a crayon. I guess my kids were in my backpack. Hopefully that's not permanent. Oh no. It wasn't me. If you take the grades. Well, that fixed it. If you take the gradient of f, well, the gradient of f at x, y, z is the vector fx, fy, fz, which means attached to every scalar field, there's this object. And everywhere you put the gradient, I mean, it's very natural to think about a gradient field associated with a scalar field, right? It's just with the set of vectors that's orthogonal to the level curves. So this thing is the gradient field for the scalar field little f. And these are pretty easy to visualize if you have level curves because you can just draw them. Any more enthusiasm. Yeah, so basically anytime you can think of drawing a scalar field, regardless of how level curves work, you know, maybe you got a little island of a level curve over here, you could just say, oh, well, whenever you take a gradient, you're going to get things that look like this. Maybe out here it points this way, and over here it points this way, and over here it points this way. But the idea is, this is the relationship. Again, I want you to think in terms of fluid. If you dropped, you know, if you wanted to, if this was a topographic map and you were looking for water flow, this would tell you what the flow lines were for water. If you're looking at electric field and you drop in an electron, it tells you how the electron will move in the electric field, main charge particle. So the relationship, there's a deep relationship between scalar value functions and vector value functions that is given by the gradient. And this is a differential relationship. In some sense, we think of the gradient field as like the derivative of a scalar field. And that's how you produce it, right? You take a derivative. Okay, now the first question that occurs to me, if somebody says, oh, it's a derivative, well, can you integrate it? Keep that in your head. Good question. Okay. So once you have this notion, once you have the notion of the relationship between a scalar field and the vector field that is produced by the gradient, you can come up with the notion of what are called flow lines. Flow lines tell you if you started at some point in this vector field and you started moving along the arrows, right? If you think about this as a derivative telling you what direction to go, if you started moving along the arrows, where would you go? And the idea is, however you move, you're always going to have to cross through the level surfaces at a perpendicular angle, right? Because that's the direction the gradient goes. So if you started right here and you passed through this level curve, you better go, let's imagine that's 90 degrees. Wow, that's pretty terrible. Whatever. Maybe something like this, right? As you leave, you cross through what the gradient field tells you. It basically tells you what direction to travel. You can imagine you can make this as tight as you want, makes this at every point. The gradient actually tells you how you flow from one point through the vector field. They're called flow lines. If you were over here, you would go this way. If you were down here, you might leave like this. If you're up here and you started thinking about flow lines, well, if you're up here, you go out, say, this way. And if you were here, you go out, like somehow you have to perpendicular here, perpendicular there, perpendicular here, perpendicular here. The fact you have to cross through these level curves perpendicularly dictates something about the flow lines, right? The gradient's always in that direction. So you imagine the gradient is dictating how you pass through all of those level surfaces. So the definition of flow line, the vector field, is a differentiable path x from some interval into, say, I guess we'll be in Rn here, but really wherever you only ever using R2 and R3. So this is true. X prime of t is equal to the gradient of f. That's a weird statement. Sorry, I think it's the green, hard to read it and stuff. X prime of t is equal to the gradient of f evaluated at the point x of t. We should think about this definition for a second because there's a lot of meat in this. So it's a path that satisfies this property. What on earth could that possibly mean? I can't just write down one of these things. I mean, I can't just write down an x and assume it's a path, right? Geometrically, what am I saying? I'm saying the velocity of the path is equal to the gradient at that point, right? The velocity of the path is equal to the size of the gradient vector at that point in the path. This is basically set up to guarantee that the velocity and the gradient match each other. So it's not just the directions match, it's that the velocities match too. So this equation guarantees that you have a path so that the velocity matches the gradient. What sorts of things do this? drop a charged particle in an electric field, it will move along the gradient. How will it move along the gradient? In exactly the same direction that the gradient induces on it, right? The gradient is telling it how to move. This is saying, so what this is saying is, you think of this as measuring what the force is doing, and it's acting on something that's moving in the vector field. So the motion of the particle is equal to what the gradient, what the vector field is saying something should do. I'm going to say this enough times in enough different ways that hopefully it's not completely confusing what I'm saying. So you have some F. F is a bunch of potentials. You can think about what F does is it gives you level curves. Okay, there's level curve, there's level curve. You have the gradient of F. What the gradient of F gives you is gradient vectors, the directions of greatest change. That gets you these guys. So at this point right here, maybe this is the point A. The value at that point is F of A. The vector pointing out of it like this is the gradient of F at A. And what we're saying is something is a flow line if whatever it does, when it crosses through this, its tangent vector matches the gradient vector. So the tangent vector of the path matches, sorry, not even the tangent vector, not the unit tangent vector, but actually x prime of t. The tangent vector, the velocity vector of the path matches the gradient vector of or matches the gradient vector. Does that make sense? I know that I'm saying this a lot of different ways. I'm not trying to be confusing. A path has the property that its derivative, its velocity, is equal to the gradient vector of the vector field that's sitting inside, the scalar field that's sitting inside. That's what this does. These are really special. Is there just one flow line? No, there's infinite. Can flow lines cross each other, you think? Sure.
They become one flow line.
Yeah. If flow lines cross each other, then you would have two gradients.
This is an open question. I'll leave you guys to chew on this, right? So this is important sort of intuition here. If I started writing down flow lines for this, what the flow line would do is it'd say, every time you're on a flow line and you cross through one of these level surfaces, if you computed the gradient in that direction, then the tangent vector for the curve should be the exact same vector. This vector and this vector should match. So there's going to be an infinite number of these through every single point in your domain is going to have a flow line running through it, all of them, right? So you're just going to have all these flow lines running all over the place. Flow line, flow line, flow line, flow line, flow line, flow line, flow line. And the question is, with no assumptions, I heard somebody say, can these cross? Actually, discovering the assumptions is the exercise, right? How do you know that they don't cross and when? Yep.
So if all the gradients are pointing inward and outward, so they all converge on a point, that is cross.
Sure, right. You can have a sink. You can have a vector field that you guys. I don't know if you guys know what a sink or a source is. If you've seen that in your stuff, a sink or a source in this language is exactly what you're describing. A sink is a place where you have a vector field piling into a point, and a source is where you have like vectors erupting from a point. Okay. Now that does not happen in a. Okay, so that. I don't know if everybody follows what I'm saying here. I'm saying what they're saying is if you have a point, say this is in the middle of this picture. This point right here seems like no matter which way you go from it in any direction, you get a different flow line, right? Because if this is all outward pointing, if we have outward pointing gradients in all these different directions, this is out, and no matter how small the circle you draw, you have these outward pointing gradients. Well, where does that point go? Well, it certainly looks like in some way, all the paths come from that point. This is a physical idea called a source. So does that mean crossing? And if it does, how do we get rid of it? Because that's not usually something we want in a lot of physical systems. Some physical systems. So again, can these cross? and when is a question that we're going to keep in mind. Okay. Okay, so with the notion of flow lines, so here's our three big objects right now. I'm going to define this now, a potential, which is a scalar field, F. We have the gradient field. Is a vector field. We define as f of x is equal to the gradient of f x. We have flow lines, which are paths. So a flow line is a path x that has the property that x prime of t is equal to either f of x of t, if you want to use the f notation, and if you want to use gradient notation, you write grad f evaluated at x of t. So our objects so far: potential functions, gradient functions, flow lines. The white function here is the potential function. The pink function is the gradient field that goes with it. The green paths in here are the flow paths, the flow lines. Okay. Right. Okay. This is actually much easier to see if I actually came up with a visualization. We're gonna see if we can come up with. Maybe you guys can just tell me how this works. Because these are like typical sort of cute examples. Suppose that I give you this following vector field: f of xy is equal to minus yi plus x j. A vector field. See what it does. If I put in 0, 0, I get 0. Okay, if you not remember, this is a vector, right? This is the same as the vector minus yx. If you prefer vector notation to component notation. So there is no vector attached to the point 0, 0. What's attached to the point 1, 0? F of 1, 0 is equal to 0, 1. Right, using pink for that. What is f of, oh, I don't know. How about, I'm going to randomly choose something. Root 2 over 2, root 2 over 2. Does that get you? Minus root 2 over 2, root 2 over 2. So that means if you're right here, you're headed in this direction. That's also a unit vector, right? How about if you were here at 0, 1? F of 0, 1 is equal to minus 1, 0, which is a vector pointing this way. So what we're doing is to each of these points, we are attaching the vector that capital F produced. This is how you draw one of these vector fields. Hopefully never again in your life by hand after we do it at the beginning here. Okay. Actually, do you guys know that you get Mathematica and MATLAB for free? Okay, those of you that don't know that, you get Mathematica and MATLAB for free. They're very useful for exploring these things. You can get it. You can get it through the portal if you don't know how to do it. So I can show you. As you keep doing this, what you're going to find is you get a vector field that has this kind of behavior. As you go out, the vectors get longer. What should the flow lines look like in this vector field? Well, if you were here, you would be going this way, but as soon as you go up a little bit, the arrow starts to shift over, right? So it turns out to be the case that the flow lines here look like this. So if you're in this field, you're sort of trapped in this completely rotational field. So the flow lines, the flow of some particle that you drop in here would be forced to travel in these circular paths. Okay? Remember, at each point on the circle, the velocity of the circle should be equal to, in the tangent vector of that path should be equal to the gradient vector. So it's telling you, I mean, this should be pretty obvious. It's a circle, right? Once you start doing this, and you go, oh yeah, here it's perfectly tangent to that circle. It's perfectly tangent. Well, I drew it really badly, but imagine I drew that so that they match each other. Down here, you've got that tangent. Over here, you have that tangent, right? The tangent vectors that come, you're saying, draw a path that has these exact things as tangent vectors. Okay. Okay. All right. So, how do we actually find them? Is the question. I mean, we did it. I mean, I like, okay, fine. You know, then in math class, somebody says, "Oh, look, this is what they are," because I drew 6 arrows and then told you the answer. Like, I can do that. But you know, when your boss is breathing down your neck, slams your paper on the desk and says, "I've got these vectors and I don't know the flow lines." You can't just draw green circles. How do we do it? How do we find the equations of these things? Oh, look, why is differential equations a prerequisite for this class? This is a differential equation. We don't know x, but we have x on one side, the derivative of x on one side, and a gradient applied to x on the other. So we actually have a setup here where we're going to come up with a system of 3 different differential, I guess 2 in this case, a system of differential equations that describes what this path is. So the flow lines, you find these are found using differential equations. X prime is equal to a function of x. So those of you that do not remember your basic differential equations, next time we'll actually go through a simple solution of this so you can see how these are very simple first order equations, but again, all of the pieces from other classes that are prerequisite here are actually active in this class. Because ultimately, we're going to have equations defined in terms of derivatives, and we're going to be doing things like integrating derivatives, and both of those are the study of differential equations. All right. Thanks for your patience. I'll have your exams prepared by